Hello everybody, I'm Marcus Voss from AXO, and today I'm going to tell you what software engineering is and how it has evolved over the last decades. This is Friedrich Bauer, German computer science pioneer, and among other things, inventor of the stack. In 1968, Bauer was the chairman of a conference that has gone down in computer science history, namely the NATO conference in Garmisch on the so-called software crisis. At that time, this crisis was seen in the fact that the development of software was no longer able to meet the needs arising with the spread and availability of more and more powerful computers. One simply did not keep up with the development of the software any longer. The development was very complex and took a long time, and when software was created, it was often very faulty and difficult to maintain. The realization at that time, formulated at that conference, among other things, we need a professional and productive way to produce software, with well-defined and repeatable processes and effective methods and techniques. Software development as an engineering discipline. And so the term software engineering was introduced. The proceedings to the conference state, software engineering is the establishment and application of sound engineering principles with the goal of economically creating software that is reliable and runs efficiently on real computers. However, someone else is considered the inventor of the term software engineering. The one in the picture on the left is Margaret Hamilton. At the time, she played a leading role in developing the software for the Apollo mission, as the picture impressively demonstrates. And over 50 years later, the software crisis is still going on in some ways. The picture on the right shows the same Margaret Hamilton 50 years later at the International Conference on Software Engineering 2018 in Gothenburg, and on the slides of her keynote, you can read what we also all know, or at least suspect. When asked about the biggest issues, software developers still often answer with points like integration takes place too late, if at all, traceability, flexibility, and maintainability are lacking, reuse is ad hoc and error-prone, even after extensive testing the software is still unreliable, and everything costs too much and takes too long. Why is that still the case? Yes, exactly. Why is that? Why is the topic of software engineering still not finally solved more than 50 years later? The answer is as simple as it is sobering. Software is complex, if only because the problems addressed by software are themselves complex, and that carries over to development. According to Fred Brooks, this complexity of software is actually compounded by the fact that it must adapt to an external environment that is random, unadaptable, and constantly changing. And in parallel with our ability to master software, both the technologies and, in particular, the quantity and size of the problems that can be addressed with software are constantly evolving. This means that the issue of software engineering will not be finally resolved in the near future, not even with the support from artificial intelligence that is expected in the short and medium term, for example, the keyword being AI-assisted software engineering. While this will certainly help to increase efficiency, it will not remove complexity from the equation. On the contrary, software engineering as a discipline must and does continue to evolve in the future. And how we got to the point where we are today with modern software engineering, let's take a brief chronological look below. Let's start with the core processes. These are basically the same today as they were 50 years ago. Common names for these core processes, which make up the overall development process at its core, are analysis, design, implementation, and integration and test. What exactly is meant by these terms? The term analysis refers to the requirements of the users or the customer. For the core process, we assume that these are already roughly known and that our task is to analyze them, that is, to take them apart. We do not consider upstream processes such as idea generation or ideation for a software product to be part of the core process. However, I will come back to the fact that these areas are also increasingly becoming the focus of modern software engineering under the heading of digital design. But what can definitely still be counted as part of the core process of analysis is the specification of the solution based on the analysis of the requirements. The term specification is therefore sometimes used synonymously for the core process. The technical specification of the solution, on the other hand, is part of the core process of design. What is created or should be created in this process is a sustainable architecture for our software solution. The topic software architecture roots in the 70s with the early bases of, for example, Dave Parnas, to the modularization, to the loose coupling, and to the secret principle, or of Edgar Dijkstra, to the separation of concerns. Starting from the 90s, software architecture developed to a substantial subdiscipline in software engineering. The third core process is then naturally the actual programming, that is, the production of code. Somewhat more abstractly, this is called also process of the implementation or realization of the concepts compiled before. One can assign the fine design of the code, for example, in form of the application of software design patterns also to this core process. And as last, the core process of the integration, that is, composition of the executable software solution from your parts and the verification of the desired behavior by means of tests on all levels of the individual unit, over integrated subsystems, components or services up to the entire system. As I said, these basic core processes, defined in this or a similar way, have not changed over the years. Those persist to be the necessary subtasks, which belong to a systematic development of software. What has changed is, on the one hand, when in a project these tasks are tackled, meaning in which periods or phases, and on the other hand, which methods and techniques were used for the execution of these tasks. Answers to the first question of when in the overall process are provided by the so-called process models. I would like to distinguish here between three generations of these process models. The first generation, we are talking here about the 70s and 80s up to the 90s, is characterized by the fact that the core processes basically also define the phases in which the project runs. First analysis, then design, then implementation, and finally integration and testing. This approach was logical at the time because engineering work in many other domains, industries, and production processes was exactly like this. Today we call such a process model a waterfall model, visually shown here, where the result of one phase is the starting point for the beginning of the work in the following phase. And in this first generation process model, the results of the analysis and design phases were essentially more or less structured documents, often with a lot of explanatory text. It is not until the implementation phase that code is created here, and only after integration, testing, and of course debugging at the very end, is the executable software produced. The fundamental problem of this approach was, of course, identified relatively early on, namely that feedback on the concrete appearance and behavior of the software is not provided until far too late. And it is not until far too late that one realizes that the actual requirements are different from what was thought after all, and that a lot of work has to be repeated for a good result. With the spiral model, Barry Boehm therefore proposed an at least partially iterative procedure for development as early as 1986. What I like to call the second generation of process models has its roots in object-oriented programming, which also goes back to the 1970s and most prominently to Alan Kay and the definition of Smalltalk. At the beginning of the 90s, one is still predominantly with the waterfall model, where the core processes are also the phases. But now one abstracts after many years' experience with the object-oriented programming their basic ideas and applies them to the earlier phases. The disciplines of object-oriented analysis and object-oriented design emerge, significantly advanced by people like Peter Code, Edward Yourdon, Grady Booch, Ivar Jacobson, and James Rumbaugh. And the latter, also known as the Three Amigos, defined the UML, the Unified Modeling Language, as a quasi-synthesis or unification of the different methods and notations. Compared to the first generation, the object-oriented approaches have now established themselves as new methods for all core processes. And the artifacts that flow through the waterfall are now no longer rather textual documents but models. Models clearly defined in terms of syntax and semantics and written down in the UML. The basic idea here is that the object-oriented code emerges in the implementation as the third refinement stage of the model, or can be generated from it completely automatically. The generic term for this approach is MDD, Model-Driven Development. In its extreme form, this would mean modeling instead of programming. OOA, OOD, and the UML are still often taught today because the model-oriented procedure naturally has the advantage of higher precision. However, the vision of modeling instead of programming was never realized for many reasons. Today, the UML is still frequently used in industrial practice, but not as a universal model in the sense that all development artifacts up to the code are UML models, but rather as a well-known and thus effectively usable form of notation for the presentation and coordination of interesting aspects from the analysis and design processes in the project. And at the end of this development, at the end of the 90s, RUP, the Rational Unified Process by Philippe Cruchton, a fundamentally iterative process model for the object and model-oriented world emerged. And this brings us to the third generation of process models and the first, which is iterative quasi by design. That is, the core processes no longer correspond to the phases of the project, but these are run through cyclically again and again within the iteration phases in the course of the project, if necessary with iteration-specific different intensity and characteristics. The software thereby develops iteratively. That means step-by-step running software emerges at the end of each iteration. And it is usually also created incrementally. That means its scope increases step by step. An important driver of this development was that the model-oriented development was regarded by many as much too formalized and complex, however also little on the actually substantial of the production of software concentrated. Coding should move back into the center, and analysis and design should be reduced to the necessary. Extreme programming, or XP, as a method, which was defined towards the end of the 90s by Kent Beck, Ron Jeffries and Ward Cunningham, provides a set of techniques for this purpose, which we also frequently use today, such as pair programming, refactoring or test-driven development. An XP consistently describes development as an iterative process that is much better suited for dealing with changing requirements and constraints, that virtually embraces change, which Kent Beck summed up with the slogan "Embrace Change." At the beginning of the noughties, and very specifically with the famous Agile Manifesto, the term Agile Software Development, or Agile, came to be used for this approach, because software development with a view to change is deliberately designed to be agile, that is, flexible. The project management method Scrum, developed by Jeff Sutherland and Ken Schwaber already at the beginning of the 90s, became generally accepted as a quasi-standard procedure for agile software development. And with the connection with principles of the lean production, and with Kanban as effective associated method, the modern agile software engineering as it is practiced today developed. We like to call the period of the spread of these techniques in the noughties the agile transformation, because here the software industry was completely turned upside down in large parts. And what are the current trends? Where has software engineering gone in recent years? On the one hand, there is the trend toward extending the scope of software engineering beyond the core processes of development. These core processes, in the sense of the necessary tasks, are, as I said, still the same. With the concept of DevOps, the view is now expanding beyond development to include the operation of the developed solution and the associated core processes. The well-known DevOps 8 shows that the green development processes, that is development, for a specific increment of our software run before the red operational processes, that is ops, that is operations, but that the findings from operations should also be incorporated into the next iteration of development. A control loop is therefore created from the dev and ops worlds, which are no longer strictly separated from each other. As far as the topics within DevOps are concerned, the core processes of development are merely weighted and named somewhat differently here. But they then combine with the core processes of operations to form an integrated whole in which software is now not only developed iteratively but also operated. And if development is now to be more closely interlinked with operations in the sense of a feedback loop, the question arises as to whether it is not consistent to see this form of interlinking out in front with those who make the demands on development and operation, that is, with the users or the customers who pay for the solution, or even more generally speaking, with the business side. And this is exactly the basic idea of the BizDevOps approach. Biz here stands for business, and the feedback loop expands even further compared to DevOps. On the one hand, in that the core business processes of the actual idea generation or the definition of the software product idea are mentally added as processes that still take place before development, shown above on the left, and on the other hand, as the findings from development and operation not only flow back into development but also into the business, shown above on the right. So we see what we call modern software engineering today is much broader and involves the participation in the engineering process of many more people than just the actual developers. In this sense, the biz and ops people are also key participants in the engineering process without having to be engineers themselves. And that leads us to the second and last current trend that I would like to point out. At the latest, when you have expanded your view to include biz, dev and ops, your view of the artifacts or results of the overall process expands from pure software to a complete usable digital product. Cross-functional product teams with members from all three areas work on the continuous iterative development of your product. If organizationally possible, this also dissolves the project idea, namely that a certain number of people work on a specific delimited result for a certain period of time. Continuous and value stream-oriented product development no longer has a defined end, and is therefore more efficient and potentially also more effective in that the entire organizational waste becomes obsolete. All the activities and efforts to set up and dismantle projects, the necessary negotiations, budgeting, etc. This fits in with Lean Startup. This also fits with the Lean Startup idea that product development is also iterative and should aim for an MVP, a minimal viable product, as early as possible. That is, a first product version for the market that has just enough features to be viable, that is viable in the market. And all the technologies available today support such a process: CI/CD, microservices, cloud-native, programmable infrastructure, etc. So much for our short journey through time. As you can see, the pool of practices, technologies, and tools that have developed in software engineering over the years is almost gigantic. And our task is to know and be able to apply the most important of them. And for that, in the next video, we'll take a look at what's involved, what's at the core, what's at the foundation for accelerated, that is particularly productive software engineering. Until then.